Every wave lifts a floating object, and then lowers it close to where it began. That motion seems to lead nowhere. Yet this ocean robot converts vertical oscillation into continuous forward thrust during both the upward and downward halves of the cycle. It can remain at sea for months without using a propeller as its primary source of propulsion. The secret is not on the surfboard-like float. It hangs several meters below the surface on a long tether. There, a rack of hinged wings converts vertical motion into horizontal pull. How can the wings reverse twice during every wave while their thrust continues to point forward? A wave glider is not one hull. It is a two-body system operating in two layers of water with very different motion. The surface float carries the control computer, navigation equipment, antennas, batteries, solar panels, and near-surface sensors. Its buoyancy makes it follow wave heave. A crest raises it, and a trough lowers it. The second body is a submerged glider, or sub. An umbilical connects it to the float, transmits load, and can carry power and data conductors. Parallel hydrofoils rotate on hinges within limited angles, while a rear rudder controls direction. Depth creates the critical difference. Wave-induced water motion weakens below the surface. The float follows the waves, while the sub occupies calmer water and has inertia and hydrodynamic resistance. The bodies do not rise and fall as one rigid object. They develop relative motion through the tether. As a wave raises the float, tether tension pulls the sub upward. As the float descends, weight and hydrodynamic forces move the sub downward. If the foils were locked flat, much energy would only move water vertically and overcome drag. Their hinges turn that oscillation into forward travel. On the upward stroke, relative water flow rotates each foil to one limited angle. The hydrofoil then develops a hydrodynamic force with vertical and horizontal components. The horizontal component points forward. When the sub reverses and descends, relative flow reverses too. Each foil rotates through its hinge to the opposite angle. The vertical force changes sign for the new stroke. But because foil angle also reverses, the horizontal component still points forward. The sub advances on both strokes and pulls the surface float with it. A test tank can raise and lower the vehicle regularly. The ocean cannot. Waves vary in height, period, and direction while wind and current act simultaneously. The robot's energy source is also an irregular structural load. If a foil rotates too freely, it can flutter, respond late, or create drag. If its hinge is too stiff, it cannot adapt when the sub reverses. Too little angular travel gives weak thrust. Too much can encourage flow separation. Rear foils also encounter upstream wakes. The tether has mass, drag, and elasticity. A crest can change reduced tension into a sharp load. Too short, and the sub stays near the disturbed surface layer. Too long and drag and coupled loads grow. There is also a basic limit. A calm sea provides little heave energy. In small waves, thrust falls. In a strong current, the vehicle may advance relative to the surrounding water yet still fail to hold position over the seabed. Wave harvesting extends endurance. It does not guarantee high speed or complete control. Biofouling roughens foils, increases drag, and changes hydrodynamic behavior. Salt water and repeated loading challenge hinges, tether ends, connectors, and sensors. A months-long mission demands reliable operation through millions of reversals. How can a mostly passive mechanism harvest irregular motion and still follow a deliberate route? The answer is to separate two jobs. Underwater mechanics harvest wave energy and create thrust, while electronics use a separate energy budget to choose the direction. As a wave passes, the float rises and tether tension increases. Because water at the sub moves less with the wave, the sub rises relative to it. This relative velocity, not absolute wave height, produces flow over the hydrofoils. Flow rotates the foils on their hinges. Stops or springs hold a working angle. Water crossing an inclined hydrofoil creates a force largely transverse to the relative flow, One component acts vertically and another drives the sub forward. After the crest, the float descends and the sub moves downward under weight and hydrodynamic force. Relative flow reverses. A fixed foil angle could reverse thrust and erase gained distance. Instead, the foil rotates oppositely. Vertical flow and foil angle both change sign, leaving the horizontal component forward. The machine rectifies mechanical motion rather than alternating current. Opposing vertical strokes become force pulses in the same horizontal direction. Several foils share the load, and the tether transfers their pull to the float. Travel direction does not have to match wave direction. Energy comes from relative vertical motion between float and sub, while the foil rack and rudder define the horizontal course. The robot can therefore follow waypoints in different wave conditions. But independence from wave direction does not mean immunity to wind or current. The controller must continually correct course, and environmental forces can exceed available thrust. Steering requires electricity, but that is a separate energy stream. Solar panels recharge batteries for the computer, GPS, rudder actuator, satellite communications, and sensors. Waves provide most of the mechanical energy for forward travel. Separating propulsion from payload power prevents the vehicle from continuously draining its battery through a large propeller. Some modern configurations include an auxiliary electric thruster. It can help in calm water, strong current, or precise maneuvering, but it does not change the central mechanism. On long missions, the float and subsystem harvests most propulsion energy directly from waves. Saying a wave glider uses no electricity is wrong. Saying electricity is not normally its primary propulsion source is accurate. The trade-off is low speed. This robot was not designed to chase ships. Its advantage is persistence. Move slowly, transmit steadily, and remain where a crewed research vessel can visit only briefly. The complete cycle can now be assembled. A wave raises the float. The tether pulls the sub upward. Relative flow tilts the foils and creates a forward force pulse. The float descends. The sub moves down. Flow reverses, foil angle reverses, and another forward pulse appears. A motion with almost no net vertical displacement becomes accumulating horizontal travel. The rudder directs those pulses along a route selected by the computer. GPS reports position. Satellite communication receives new waypoints and returns data to shore. Solar power sustains the electronics while wave energy performs the largest mechanical task, moving the vehicle through water. The two-body architecture is also a measurement platform. The float observes weather and surface conditions, while the tether and sub support sensors below. Such vehicles have measured temperature, salinity, ocean chemistry, biological sound, and weather in remote regions. Every benefit is conditional. Endurance depends on sunlight, sea state, sensor load, biofouling, and maintenance. Route keeping depends on modest thrust relative to wind and current. A wave glider does not replace ships, underwater robots, or fixed buoys. It fills a gap by providing persistent mobile presence with little stored energy reserved for primary propulsion. The loop closes not with a stronger motor, but by using ocean instability itself. Waves create heave. The tether separates motion between two depths. The foils rectify it into thrust, and the electronics merely aim that thrust toward the place that needs to be measured. A wave glider moves forward because it does not resist wave motion. The float follows the surface. The submerged glider provides a reaction body in calmer water, and hinged hydrofoils reverse angle so both upward and downward strokes generate forward force. Waves provide motion. The foils rectify it, and the rudder turns it into a route. It is neither a fast ship nor an unlimited energy machine. Its value is a deliberate trade. Sacrifice speed for endurance, converting every rise and fall of the ocean into another small step forward.